I'll talk about quantum compass models, which were basically the last slide, the last talk. And then talk about some concepts. I will not go into proofs, just to give you the ideas of what these things mean. Order by disorder, the symmetries and degeneracies that you find in compass models, which are sometimes called intermediate symmetries, intermediate between global and local, intermediate between global and gauge symmetries. And then I'll talk about the e.g. Chomsky Hamiltonian, and also try to say how it is relevant for real materials. Okay. Quantum compass model. So the last slide I had before talked about 120-degree compass model, which means that you have 3 directions in space, and along each direction, interaction is different. And you can find those interactions. So T gamma, by considering first the z direction, where this theta is 0, and then by doing this rotation that I got going in the previous lecture, you can generate the interactions along the 2 other Cartesian cubic vectors. Okay. And the problem is, as I pointed out, or the point is that there's always some degeneracy in this model, even if I'm on a bipartite lattice, because the interactions are frustrated. Okay, now the question is, what type of order, or orbital order, or compass order, if you want, will I find, do I expect in this Hamiltonian? So the first thing I will do is rotate my Hamiltonian by this phi equal 2 pi, which just introduces a minus sign on one of the sublattices. So there, Tx goes to minus Tx, Tz goes to minus Tz, and I do this so that only one of these guys changes sign, and then I get a minus sign in front of my Hamiltonian. This I like because now if I look at ordered states, instead of looking at staggered ordered states, I put j equal to 1 here. So if this is a positive number, then these guys want to have different signs. So there will be some staggered ordering going on. I want to get rid of that trivial ordering, let's say, introduce a minus sign, and instead talk about constant orderings. So t on each side wants to be in the same direction. Ferromagnetic Ising, like along the z direction, a bit different along the x and y direction. Now this Hamiltonian, actually, I can write in this way: Ti minus Ti plus gamma plus E gamma squared plus a constant. And that's because, well, of course I get a cross term that I like, that gives me this Hamiltonian with the 1/2 sign, and I get also the squares, but the squares, and that's similar to what Christian Batista showed yesterday, the sum of the squares of gamma of the 3 directions actually is a constant, 3/4. So this constant is there. So that's nice actually, because now my Hamiltonian is square. And we know, therefore, that it's trivially bounded from below. So if I now look at the classical ordering, if I take T to be a classical factor, I can see that the classical energy is bounded from below, 0. So my ground state has energy 0. Okay, that's good. Now next question, which is my ground state? Which vector wants along which direction does my t vector want to order? And you see here actually, it doesn't matter. This thing is always 0 as long as t gamma I is equal to t gamma I plus E gamma. So if on a side and on its nearest neighbor, the t is pointing in the same direction, this thing is 0 and I have a ground state. So I have a very huge degeneracy of the ground state. Yeah. So any homogeneous ordering vector, where Ti and its neighbors have the same ordering, has the same energy. So actually the classical ground state energy is rotational invariant. And again, this rotational invariance is not because I put it into the Hamiltonian, it comes out because I look at the ground state of this Hamiltonian, the classical ground state in this case. That's exactly what I said. The classical Hamiltonian itself does not have this invariance, which is different from Heisenberg Hamiltonian that does have explicitly this invariance. Here it is. Okay. So this means, from this, you can conclude that the excitations of this 120-degree model have to break rotational invariance. It's just somehow a coincidence that the ground state has this invariance, but excitations in general cannot obey this rotational invariance. So now in the plot, hand waving, this will lead me to order from this order. So I'll be a bit hand waving. So now let's look at the contour plot of the free energy landscape, which is this thing. So AI is not artificial intelligence, but it's artist impression in this case. So this is the very poor artist impression. So you can think of this as a Mexican hat looking from the top. And the T vector is in this valley, in this red depression, and can rotate around. And we know that, for instance, if you have a two-dimensional, this could be the representation of a two-dimensional Heisenberg model. And we know that the two-dimensional Heisenberg model at finite temperature, for instance, does not order. Yeah? The fluctuations are such that this guy starts rotating around. Now, if I look for make the same picture for the 120-degree model, again, if I look only at the ground state, at the red here, you see that the red thing, the red path is a perfect circle, again, like it was here. But the excitations, if I go out to the edges of the Mexican head, they are not symmetric. And actually, if you look at this region, for instance, locally, the space is very flat. The landscape is flat, which means that's good for excitations. If I look at excitations, the phase space for excitations here is better than when I wrote this by 30 degrees, because there the values are much more pronounced and deeper, and there's less phase space for fluctuations. So if I look at fluctuations, this ordering factor actually wants to stay around here. So this, well, actually, why is this relevant for the 120-degree model? I will not show this, but actually, if you calculate the fluctuations of this 120-degree model beyond the classical ground state, you will see that there is no classical ordering. Like in the two-dimensional Heisenberg model, the three-dimensional 120-degree compass model has no long-range order at finite temperature. Yeah. From a naive calculation. Now, if you do a not so naive calculation, and you take into account this order by disorder effect, well, you see that excited state break rotational invariance, so there can be a simply breaking, which is ordering at finite temperature because of the finite temperature. Which is order by disorder. The fluctuations break the rotational invariance. And actually, with Zohar Nusinov and these mathematicians, Bliskop and Chase, they have proven, actually, that there is a finite temperature phase transition in this classical model. This is a 60-page proof, actually, so it's a big thing, but it's non-trivial.
So this is classical, what about the quantum fluctuations?
The quantum fluctuations. Good question. That's next thing. But let me say one picture with the 120-degree compass model. So if you have proof, if there's a proof, there is an ordering temperature, or an ordered state, finite temperature. And the question is, what temperature does the phase transition take place? And this is a Monte Carlo calculation in a group of Simon Tripps. And you see that, okay, this is the order parameter, and for this 120-degree model, you see there's, for different lengths or system sizes, there's a very nice drop-off here. So there's about around 2/3, there's phase transition 2/3 T over J. They call this JZ, which is a detail. So indeed, there is a finite ordering temperature. Now quantum, what happens if I don't look at the classical state, but I look at the quantum fluctuations? I go again to my T1/2, not to T infinity, my classical vector, but T1/2. Well, you would already expect to find a similar thing, right? I mean, if I have a classical system at a finite temperature, those fluctuations probably are similar to the quantum fluctuations at zero temperature. Well, what you can do actually is first calculate we call this orbital excitations, because this describes orbitals, or the elementary excitations. If you do this on the most naive level, actually you will start with the classical ground state and calculate the fluctuations and like a spin wave, orbital wave, expansion. And you see the important point is actually their gaplets, which again is a coincidence. It's not a Goldstone mode arising from a rotational symmetry that's broken. It's this pseudo Goldstone mode that arises because the ground state manifold has rotational invariance. You can see actually if you look at the fluctuations, there's the energy, so the energy of the quantum fluctuations as a function of this rotation angle, and you see that for this case zero angle, the quantum fluctuations are largest, negative, and then here it has a sign line behavior, meaning that quantum fluctuations actually will favor some kind of ordering. Well, this at discrete angles, either 0 or pi over 6 or pi over 3, and so on. So again, the quantum fluctuations break the rotational invariance.
So what is the complete spin wave for you to shape the system, right? For you to shape the mountain, right? Then I would have also got a small right? You should enter some parameter, like phi or whatever.
Yeah.
So why is it strange that I got this?
Well, if you do a spin wave calculation for an Ising model,
No, but Isaac is discrete, right?
yeah, but why my model is discrete as well.
That's not referenced.
So this is my 120-degree model, where I have the Ising-like interaction along the z direction, and an Ising-like difference, but again, Ising-like interaction along the x, and again, a different Ising-like interaction on the y. If I look at each axis separately, I have an Ising interaction along that axis.
Okay.
Yeah. So, okay. So that again gives you the idea there could be some order from disorder going on here, but now on a quantum level. And the Traipes and his co-workers also looked at the quantum problem, and okay, this is for, they truncated the model, they changed the model a little bit because there's a problem with there's a sign problem in the quantum Monte Carlo, and so on. So you start simplifying the model. The important thing is that this Hamiltonian is realized when Jx over Jz is equal to 1. And you see here actually what's calculated is the gap. So you see, or at least within the accuracy of their calculations, there are 3 years a gap, at this point, which is about j over smaller than half j. Yeah. So that's different from this picture. So the fluctuations actually generate a gap here. And you see that this j x over jz equal 1 point actually just on the border between two ordered states. So it's really at a quantum critical point. So it's quite rich. Okay, so now I have a small intermezzo saying, okay, that's this order from disorder in this classical model. Is that relevant for anything in real life? It's very idealized, if you want. Well, and it also, in this, what I will do next, I can connect to the Young-Teller effect. This has again to do with these orbitals and orbital splittings. So as was in the recent session yesterday, if I have these EG levels in the octahedral symmetry OH, and I break that symmetry, yeah, by going to V4H, by for instance elongating these the bonds along this direction, then what will happen is that in this case, if bonds are elongated, this cigar shape, the 3z squared minus I squared orbital is lower in energy. If in the plane the bonds are elongated, this x squared minus y squared orbital will be lower in energy because of this. I like this because that's like yesterday, because of this Coulomb interactions. Yeah. So there are two possibilities: either elongation in the plane, x squared minus y squared lower, or elongation perpendicular to the plane, then the 3z squared minus r squared is lower. And this is for manganese, where I had this filled core of T2Gs. So I forget about the T2Gs, which also split up, but let's not go into that. Okay. So what is the consequence of this actually? Well, it gives rise to a local Young-Teller instability. It leads to a Young-Teller distortion with an amplitude Q, where Q parameterizes the size of this distortion. Why? Because the energy lowering due to this distortion is proportional to Q. I have degenerate states and I split the degeneracy. So the energy I gain is proportional to the split, to the distortion. Instead, the kinetic energy that I lost in making this distortion, I don't know what it will be, but I'm sure it has to be proportional to Q squared, to the square of the distortion. So my total energy, very roughly, is minus alpha Q plus beta Q squared. So I know that there is always a finite distortion present. The system wants to distort at a finite Q. And where this finite Q is, that depends on this alpha and beta parameter, of course. So no matter how small the Young-Teller coupling, always a finite distortion. Okay, that's for a local Young-Teller impurity, as it is called. Now,
Question about
sorry.
plot. The E total, when Q equals to 0, the E total equals 0. So the red line should go through 0.
Yep, you're right. Schematic picture. But you get the drift, right? Also without that picture, you're right. Okay. So that was a local distortion. Now I'm on the lattice, I have this manganese 3+, which has a D4. If I have distortion on one side of this oxygen O6 octahedra, then by definition I also change the oxygen octahedra on the side next to it, right? The distortion on one side is the distortion on the other side, or on the neighboring sides. So there are two kinds of distortions, which are called Q3 and Q2, again for reasons beyond my comprehension. This Q3 is mainly out of the plane distortion, with oxygen moving out, and in plane they're moving in somewhat. And this Q2 is two guys in plane moving in and the other two guys moving out. Now, if I have a distortion along the z-axis, or the c-axis I call it here, this is Q3. And you can easily see by some geometry that a distortion along the b-axis here will be Q3 plus square root of 3 Q2 over 2. Now this thing we have encountered before, right, this combination. And along the a-axis is Q3 minus the square root of 3 Q2 over 2. You see, this is the square root of 3. That's important. In other words, now I look, okay, so these are these rotations, and this also because this is an EG group. Question?
Yeah, in the QB and QA, should there be the upper and bottom panels? Are they displaced at all? Or is it just side arrow?
They're sitting there.
To the top and bottom?
At the Q2. I think they're just sitting there.
But how much for the QB and QA?
So in the QB, well, these small arrows here, I just suppressed in these pictures. Otherwise it gets too cluttered. So the Q3 has this also this in-plane distortion. It's this 3z squared minus r squared density. So, and if you wrote, you would see, I have to move this guy in. Let me come back to it. I thought that they were just sitting there, but you might be right actually that they have to move somewhere.
But the first order they sit,
I think it's it. Okay.
because by this you will conserve the volume. I mean, the only
Yes,
thing you have
exactly.
to conserve is the volume, so
Yeah.
it's,
That's a good argument. This is the volume conserving. It has to be. Yeah. And then second order is not volume conserving, and that's why actually you have this finite temperature, or due to finite temperature always have this occupation. Right. So the point I want to make here, well, now I also know if I have two of these guys sitting on top of each other, if I have QC on this side, I will have QC on the side above it. Well, minus QC, just in the opposite direction. And the same here along the b-axis. I have elongation along the b-axis here. The guy next to it will have the same elongation, well, other side, some compression, but along the same axis. Same thing goes here. So what I constructed here, well, this Q, C, A, and B are again on the units, on the 1 unit sphere, on the circle, and I know my interactions. Oops. Yeah, my Hamiltonian for this lattice system of Jan-Teller sites is QA, QA, QB, QB, QC, QC, which is exactly the EG, the classical 120-degree model. Yeah? Where, again, I can just write this as the sum of squares, and I can do my whole thing, my whole spiel about order from disorder for this system now of EG distortions, which are basically classical objects. Yeah? Distortions have a big mass, the oxygen mass comes in there, the quantum effects for this EG, in this EG manifold this can be neglected in first approximation. That's two very good approximations. Okay. So I talk a bit about this 120-degree quantum compass model, but you can, the most natural thing to look at actually is a 90-degree quantum compass model, which is even simpler in structure, conceptually, which means this 90-degree means I have Tx along this axis, Ty on the other axis, and Tz on the axis perpendicular to it, which has a very similar structure now. I can write it down in the same way as I did before. It is T gamma I plus T gamma, where this gamma is 1, 2, 3, and these E's are just the 3 axes. Yeah. So, okay, why do we do this? Because I want to illustrate another point. I want to illustrate that this EG model has some extra discrete symmetries in there. And that's the same thing goes for actually the 90-degree model, but easier to show in the 90-degree model, so I'll use that as an example.
Can I ask a question?
Yep.
So this corresponds to the p orbitals, basically. No?
Good question. Answer is So p orbitals, if you have 3 p orbitals, you have 3 possibilities, right? So I'm talking about SU2 here, a spinor that has 2 components. SU, and you have a spinor with 3 components, you'll go to SU3. So for p orbitals,
But you have here x, y, and z, so...
yeah, it looks, I mean, you would say this looks, and my hope would be very nice. Okay, for T2G orbitals I have this Hamiltonian. I would love it if that would be the truth, but it's not. T2G or P orbital, which are, again, there's a manifold, are 3 component spinors, right? Unfortunately, it's not. But it is realized in a different context. I'll come back to that. Okay, just want to show that these compass models in general have symmetries that give you cute, interesting physics. So I can look at this compass model now in 2 dimensions. Which is a bit tougher to do for this EG model because I always need the 3rd dimension to keep the model symmetric. But here I can just kick out the z-axis and still have now a 2D compass model on an n-by-n lattice. So for instance, the x is operative along these horizontal bonds, ty is operative along the vertical bonds. Now let's put in a spin structure. For instance, I put all spins here along this b-axis. So everywhere Ty is operative, which means I can forget about Tx. They do nothing. They don't contribute anything to the energy. Just at the classical level for the moment. Everything I will say, my conclusion will be true for the quantum model. I can take a different ordering, for instance, along the A direction, and there, in turn, the Ty will not be operative, but the Tx part of this Hamiltonian will be operative. And actually, on a classical level, it's obvious that if I go from, make a rotation from spins along the B to along the A, I always pick up part of Tx, part of Ty. They compensate, it's a cosine squared plus sine squared, and I always get this rotational invariance, you know, that's produced in this way. Okay, but now I'm here, I'm not going into that physics. I'm looking at, okay, I have an ordered state here, which is ferro ordered. What happens if I now turn around 180 degrees, these spins on one row. And the answer is nothing. Ty was not operative here. Yeah. So only tx is operative. Well, I change two spins here, actually all spins get a minus sign here. So my Hamiltonian is invariant. And actually you can show this is the case for any orientation of those spins. This, you can also write it down nicely in an operator form and construct an operator that's produced with your Hamiltonian, and you see that this operator is reflections along the b-axis or reflections along the a-axis of any column. Yeah. I can do this for any column.
So the generic is like 2 to the number of rows?
Yeah, 2 to the number of rows. Yeah. So this is a huge degeneracy of the system. And what's interesting here is this was coined by Zohar Lusinov, who was the first one to point out these things, I think, and his co-workers. This is a symmetry that's between global and local. So the gauge symmetries that also we've heard about are all local symmetries. Yeah? You can locally, you have invariance. That's what you don't have that here. In general, you don't have that in spin models, unless you construct spin models that do have that. You can do that, of course. So that's not this symmetry here. You can have symmetries that are global, like my magnetization. That has a direction. That's the global symmetry of the system. And this symmetry can be broken, this rotational symmetry of the whole order parameter. This situation is actually in between. It's not you don't have a global symmetry, you don't have a local symmetry, you have an in-between intermediate symmetry. Okay, that's putting a word on the thing. What is the consequence? Well, the consequence of this intermediate symmetry, actually, the expectation value of any magnetization is 0. So you say, okay, I want this I define as being my magnetization, and I calculate the expectation value that is 0. Why? Because any state that has this symmetry, the spins along the x-axis will equally come into the partition function as the one with all the spins flipped. So in the partition function, this thing, if you look at just calculate the expectation value, is 0 by definition, or actually by symmetry. So can there still be order in this system? And that's also this. Tom mentioned this. Well, you can. You can have nematic order instead. So it's not the first moment of t that orders, but the second moment, the square of t that orders. And you can easily see that the square of t can order because it doesn't differentiate between all spins to the left, all spins to the right in one row. Yeah. It doesn't differentiate between that, but it differentiates between spins in the plane or spins rotated out of the plane. And actually it turns out that spins here, the nematic ordering prefers the spins being in the plane. I'm not saying which direction, but either along the plus or minus axis. Or equivalently rotated by 90 degrees. Okay.
May I ask a question?
Yeah.
And in this picture, if you have quantum fluctuation, once again, quantum fluctuation can choose some real order of the first one.
Yeah.
That's only on the level of the classical ground state.
Yes. So you perhaps would say, wow, now I have a nematic order parameter. And so this is kind of discrete. I could have ordering at finite temperature. This looks like an Ising model. You know? This is an Ising model. Well, it is. It's an Ising model of one dimension, I think. So in the end, you don't get any finite ordering temperature here, if I remember well. But
you can create the solid on those fields with the local energy cost, and then so at any finite temperature. That's the reason why you're
exactly. Yeah. So I can. So the first thing is making the argument that okay, instead of having these spins to the left, I can make these spins pointing to the right. Right. Well, that costs me an energy. That costs an energy J or 1. Yeah. But at a finite temperature, I have very many possibilities to doing that. Well, I have n possibilities of doing so. So the entropy always wins over this finite energy. and not E. So you don't, I think you don't have any finite temperature phase transition here. Just to give you a flavor of this compass model, well, you can also take this 120-degree compass model and not look at it at the cubic lattice, but rather on a two-dimensional lattice where I have three factors, the honeycomb lattice. That's the most natural, actually, setting of this 120-degree model, right? And this was done, not by us, way before, or 2003, by Kitaya. And he looked at this model because it's a model you can use for topological quantum computing. I'll say nothing about this anymore. It's very interesting stuff. You can solve this exactly in a wonderful mathematical way. Just to say, it's a realization of a compass model, only on this honeycomb lattice. Okay. This is how it looks like. So, just to give you a flavor, these quantum compass models can describe what? Well, I've introduced them in the context of this orbital super exchange, but also same goes for collective Jahn-Teller effects. If I'm looking at the EG orbitals, Christian has shown that these compass models also appear for if I describe electronic orbital current and polarization in mod insulators. So they appear in quantum computing, so say Kitaya. Actually, this thought that these compass models again extended somewhat, but the compass model are the core of describing the exchange interactions in this iridate, this 213 iridate. This was by Pinet Kaludin, was the person bringing this forward. Of course, anything that can be realized in a solid state nowadays can be also realized by cold atoms on a lattice. This was first Eugene Daimler proposed this actually in the context of Kitaya's model. And also, if you consider coupled Josephson junctions, actually you can realize this 90-degree compass model, which was pointed out by Joe Moore, co-workers. So these guys appear in a broader context. Okay. Last part is the Chomsky Hamiltonian. So I've shown you that these models, compass models in themselves, they tend to order by fluctuation, by some kind of fluctuations, which makes them very susceptible to some kind of perturbation. If I go away from the perfect symmetry that I introduced, probably the system will tend to order. So one of the symmetries I introduced in the beginning to derive this EG model is say, well, I'm dealing with spinless fermions. But in general, of course, these fermions do have a spin. And I have to take that into account, because this changes the super exchange. So now here, I consider two electrons on the same side. They have energy U, and I do not consider the Huntsville coupling. I just forget about that complication for the moment. Only spins and this energy U, where this U prime is equal to U, which is another way of saying that I forget the amount. If electrons are in different orbitals, I have this old result. Along the z direction, I have TZ, which is not dependent on the spin direction. Yeah? The different orbitals, I have the old situation again. But now if they're in the same orbital, of course, these two spins are both in the z orbital, two electrons both in the 3z squared minus r squared orbital, I have super exchange. And it's a regular super exchange as in the hard model, as if I'm dealing with one orbital. One electron here, or let's say one electron here, one electron here. These guys are not hopping at all, and there are also no electrons. So I have just my super exchange t squared over u. Or as the Heisenberg Hamiltonian describes this bond. Yeah. So now I have to combine these two observations, and I get that along the z-axis I have super exchange of Heisenberg type if both TZs are 1/2. If they're both up there. So this is the expression. Plus just the one I had before for the spinless fermions. I can just add this up in a nice way, and in the end I get this expression. So along the z-axis I have super exchange at a la Heisenberg plus 1/4. Actually I have minus 1/4 before in the Heisenberg model. Now I have a plus 1/4, and we'll see this is important. It just comes out of these manipulations that down there that I did. And this is, well, if both electrons are in the 3z orbital, and this is, if I should do, I just kept this in there. Again, the sum over these guys is 0. If I have this Hamiltonian, I can generate the Hamiltonian along the x direction and along the y direction by these rotations that I got going last time. And this defines the E.g. KK Kulichomsky Hamiltonian, which is this guy. Up to a constant because, like I said, the sum over these t's, as Christian also showed, is 0. And again, the same definitions I had for the E.g. So that's pretty nice. That's pretty quick to derive this KK model. Now the question is, how do the spins and orbitals not order in this case? My model is SU2 cross SU2. A bigger phase space now, a bigger space. So how do these guys order? Well, one observation is that I can look at the Yale state with perfect antiferromagnetic order, no fluctuations. So that Si dot Sj is -1/4. Well, let's do that. Well, if it's -1/4, the Hamiltonian here vanishes, right? So the Yale state is not a good state. Well, it has 0 energy. Maybe it's the best of all the bad states, but it does not look like a good state. It doesn't give much energy. However, if I look at these operators here, I see that it's a half plus something, half plus something, which is bigger than or equal than 0, when the something I add is bigger than -1/2. So this part, let's say, in general, is bigger than 0, which means that this part wants to be smaller than 0, which means the spins want to be antiferromagnetic, so the spin ordering must be antiferromagnetic. But the perfect Néel order was out. Yeah? So what the solution is, or at least the theoretical solution is, that you get an orbital ordering these t's in such a way that you form kind of pseudo one-dimensional spin chains. So you get a lot of fluctuations in this one-dimensional chains that form spontaneously. And these fluctuations push this Si dot Sj from -1/4 to something lower, and therefore you can gain energy. Again, these fluctuations, now spin fluctuations, drive the ordering of both the orbitals and the spins. So along such a chain, this exact expression, and again, the ordering arises from interplay of spin and orbital fluctuations. There's no proofs out here. This is put forward by Kalul and Udafenko. Would be very nice to have something. It's a very good idea. There are some approximate calculations showing that this is the case. No proofs as yet. Okay. Last thing I wanted to talk about. So again, I have now introduced a new set of degrees of freedom, which are my spins, but they don't help in ordering. Well, the fluctuations of these guys help in ordering, but these, again, because it's the fluctuations, they will be sensitive to some kind of perturbation. What's the most relevant perturbation? Well, actually, this Hunt's coupling, right, that I neglected. So instead of the intermediate state, if the spins are different, they have energy U, but if the spins are the same, the intermediate state is U minus the Hunt's rule coupling. That's the next perturbation we're going to look at. Well, Hunt's rule coupling normally is much smaller than U, so here the J is 4t squared over U. In this case, the J is 4t squared over U minus J Hunt, which I can expound in J Hunt over U, which I call the parameter eta. So the question now is, how does this eta J part, because of, related to the Hunt's rule Hunt's rule coupling, affect my Hamiltonian, and actually here's the answer. You can do the same tricks I did before and derive this. So now you get this KK Hamiltonian, which is the old part I've shown before, plus eta times a part that takes care of this Hunt's rule effect. So now let's see what kind of ordering do I get. Here's this Hamiltonian again. If different orbitals are occupied, then TC minus 1/4, this is minus a quarter, smaller than 0, so then the spin exchange is ferromagnetic. So TC minus 1/4 here, this thing is negative, so the spins want to be ferromagnetic. So again, different orbitals occupied spins ferromagnetic. If the same orbital is occupied, that's the situation as we had before. Same orbital occupied, TZ minus 1 equals 0 in this case, and we go back to the, or this eta part vanishes, and we go to the old situation where we said that spin exchange wants to be anti-ferromagnetic. So here we have now a very simple rule, and okay, this is known as the Goodenough-Kenmore-Anderson rules for super exchange. I derive this now in the context of e.g. orbital degrees of freedom, and under a lot of restrictions, but it's a very general result. And the very general result is if different orbitals are occupied, spins want to order ferromagnetically. If the same orbitals are occupied, spins want to order antiferromagnetically. Is this relevant for anything? It's relevant for a lot of things. This is one, which is length of number 3. You see here the orbitals are staggered, spins are ferromagnetic in the plane. Between the planes, orbitals are ferro, let's say same orbital occupied, spins ordering is antiferro. That's what I have to say.
Thank you very much. For a couple questions.
Normally so loud, and now so silent.
How about some student questions? All right, we have a taker.
Could you explain in a bit more detail the difference between the 90-degree and the 120-degree?
Yeah. So the difference in the Hamiltonian is in the Hamiltonian, where actually in the 120-degree model, along the 3 Cartesian directions, they exchange the operators, spin operators, or pseudo-spin operators, are equipartitioned on the unit circle. And the
You know, maybe it's better to write it on the board.
yeah, okay, I can also go back to this picture, but I just want to say in a bit more formal way, it doesn't go very well with pictures. That's this. So this is the exchange. Well, now this is for this exchange along the C direction, and now along the A direction, which are orthogonal to that, is 120-degree rotated in spin space, in pseudo spin space. The spin arm is rotated by 120 degrees, but the spin arm is on the unit circle. So one way of thinking about it, I have 3 Cartesian directions, which I have to partition, and which I have to describe by an angle. And this angle is on the sphere. So the only way I can do this, honestly, is partitioning not the sphere, the circle into 3 parts. And that's it. So now if I go to the 90-degree model, I'm not on the circle anymore, I'm on the sphere. And now I can partition, so along the z direction, I can have tz. I can, along the x direction, having dx. Along the y direction, have dy. I have an extra rotation axis, if you want. I've introduced an extra rotation axis. Okay. So that's the difference. But there are more differences.
Do you have any information about the finite temperature phase transition about the Fourier-Komsky-Hamiltonian?
I don't. So it's okay. Daniel Komsky and Google have introduced these models in the 70s. There's a beautiful review paper in 1982. So it was where actually also this word compass model was also coined. Actually, this 90-degree compass model was also already mentioned there. And so that's almost 30 years ago now. And so you would say, you would expect that people did a lot of that. It's a very accessible review paper, but somehow it's within the sphere of people looking at real materials and ordering all this stuff is known, well known. If you look at the real theoretical, or at the formal theoretical physicists, little has been done on these models. And one reason is, I think, it's rather complicated intrinsically, and only with the modern quantum Monte Carlo codes, you can start hitting these models and looking for phase transitions in an unbiased way. So that's why in the last, say, 5 years or so, there's much more is done on these models. But you can imagine, look at the EG model, 120-degree model, without spins. It's already, from these quantum Monte Carlo guys, it's a big job, and you saw this is right at the phase transition. So now if you introduce spins on top of that, this does not get better. But probably somebody doing numerics will can have a better answer, or maybe there will be algorithms that are more efficient. There's a lot can be done there, but so there's no information.
So it's a kind of intriguing remark that these models, some of them have symmetry, which is intermediate between local and global gauge symmetry. Does that have any implications for the types of topological defects you would find compared to ordinary spin models?
Christian says yes, so we have to explain why.
No, right, because for essentially when you have intermediate symmetries for order parameters that break those intermediate symmetries, the topological defects that you have are the typical topological defects in a dimension that corresponds is determined by that intermediate symmetry. I know it's a complicated statement, but if you go back to your slide on the blue, so the intermediate symmetry that Jerome described is one dimensional, right? So you can flip all the spins on a one-dimensional
For that
shape.
model, yeah.
Natural, if you have discrete symmetry in 1D, the natural topological excitations are solitons, right? And here we are as well, so it creates a soliton in those blue spins. You have a local energy cost, meaning that these solitons will proliferate at finite temperature. So although you have a 2D system, you have low energy excitations that are characteristic of a 1D system, and that 1D comes.
Is that peculiar to the 90-degree model, though? I mean, do you get, if you have 120, then you have something else, right?
You have the same. On the square lattice, you have the same because you have an object which you can rotate. You have some plates because it's unconnected. You have some spin projections which are not interacting along certain direction, and then you can have a plane which you can rotate, and that costs no energy.
So the general remark is you go from dimension D to dimension D minus 1 if you have one intermediate symmetry. If you have two intermediate symmetries, you go to dimension minus 2. So the effective dimension is reduced. And in a rather precise context, we can do precise statements about it.
But will it be correct to say that everything also depends very much on the lattice? If it's a bipartite, or if you go to the parallel lattice, then you don't have these objects which you can rotate, and then the symmetry becomes discrete, and you don't have even this intermediate. You have a discrete symmetry, not this intermediate symmetry.
You're right. I mean, it's not by definition that if you have these models, you have by definition a intermediate symmetry. It depends, of course, on the connectivity of the lattice and all that. But actually, yeah. So there.
Coffee. That's a good coffee discussion. One last question.
The ordering that you mentioned for the pseudospins here, can you detect these? It could be a naive question, but
yeah. So the theoretically very easy, but so experimentally the question is, okay, how given your system where this is realized? So this is actually the Joe Moore. If you have a p-type superconductor and make Josephson junction out of those, and you couple those, you get this model. In a lattice, if this would happen, actually you would have dramatic ordering going on. So which means you get the symmetry breaking from D4 to D2. So that would be, let's say, most generally the experimental signature, a lowering of the symmetry from 4-fold rotation to 2-fold rotation. because of this nomadic order.
Okay, let's thank Ruben again.